Okay, so we are live.
Mm-hmm.
So guys, our today's lead code question is counting number of bits in an integer. So we have been given an integer. Let's assume we have been given 11. So what says binary representation? It is 1011. So what we need to do is we need to calculate number of ones that are present in its binary form. So for example, this number 11, we have been given 3 ones in its binary form, so we need to return 3 as the output. If we see the question, there is a lot of confusion in the question that here in the integer it's showing that we haven't given a number in a binary form, but it's not the case. If we see about, we have been given a number in its integer form. From that we need to check that we we need to check about number of ones in its binary form. Okay,
Okay.
so how we can do it like that. We can just first of all initialize the count variable as c equal to 0, and we can check if it's so. What this n and 1 do is it returns 1 if the last bit of a number in its binary form is returning is 1. If it's 0, then it will return 0. Basically it will return the last bit of the number in its binary form, and after that we can just left shift a number, right shift number by 1, and we can simply return c. So let's check. You can see it ran successfully. Let's submit it for all the test cases. So yeah, it got submitted. Okay, so now to you, Sangam.
Okay. So guys, to the question that we have been asked today in our today GFG PODT is that we have to figure out that if a given graph is Euler circuit or not. So what does that means? So yeah, this is the question that we have been given, that while returning the answer, we have three options in which we can return the answer. The first one is that we can return the answer in the form that the graph is forming in Euler path. If it is, then we will simply return 2. If it is only forming a Euler circuit, then we will return 1. And if it not forming neither Euler path and nor Euler circuit, we are simply going to return 0. So now before we went on to like how we are going to do in this case, let's just first of all understand that what is Euler path and Euler circuit. So guys, as I've already written here, see, Euler path is nothing more than just a graph in which every vertex of the graph is visited by only one time. Like we are not going to a vertex again and again in a Euler path. It is just a simple path in which every vertex is there and we are just visiting them only once throughout our whole iteration. So as you can see in our example, this I have already written here that 1 2 3 4 are the vertices of our graph, and if you observe it carefully, each vertex is visited once. So let's just say we are going to start from 2. So we are first of all going to 1, okay, so then 2 and 1 are visited, then we are going to go to 3, then yeah, 3 is visited, and then we are going to go to 4. So this way you can see that this graph is only visited by 1. And even though yes, we have start from 1, you can see that from 1, yes, we are visiting from 1 to 2, so visited only one time. Then from 1 we can actually go to 3, so that is 3 is visited only one time. And then from 3 we can go to 4, so that is 4 is visited only one time. So in this graph, each vertex is visited only once. The same goes for this graph. We can start from 2, we can go to 2 1 3. We can start from 3, we can go to 3 1 2. Or we can start from 1, then from 1 1 will go to 2, and 1 will go to 3, and the result will be that we are going to get in Euler path. Now we have learned that what is Euler path. Let's just understand that what is Euler circuit. So see guys, Euler circuit is actually an Euler path, but the main trick in Euler circuit is that if I'm starting from a certain vertex, then I will travel to all the vertices of that graph only one time and eventually end up with my starting vertex. So what does that mean? Let's just understand it by the help of this example. So let's just say we are going to start from 2. Now if I get started from 2, and let's say I traverse first of all to 1, then I will go to 3, and then I will go to 4. Then after that, what is? I can from 4 traverse directly to. So as a result of which I am traversing to each way, I will end up on 1. So that is what Euler circuit and Euler path is all about. Now question arises that yes, if each vertices of a graph is visited once, and yes, if they are starting from a certain point and ending at a similar point, then that would be Euler circuit. Then what are the graph which are not Euler path nor Euler circuit? So let me help you in understanding that thing too, guys. So as you can see in our graph here, which I have circled here, you can see that we can visit from 1, we can visit to 2. Okay, so 2 is visited only one time. Then we come from 1 visit to 3. Okay, so 3 is only visited one time. But if you observe it carefully, you're going to find out that 4 is not visited neither by each of the edges. So as both of the conditions state that in Euler path, every vertex should be visited exactly once, and to be an Euler circuit, every vertex should be visited once, and it should begin and end at the same vertex. So as you can see that it is not happening here. 2 4 is not visiting by any vertex even exactly for one time. So as a result, this is not our Euler path, neither our Euler circuit. Now as you can see in our this vertex, so here, yes, each vertex is visited by many, by all the other vertices. Like one is visiting to 2, one is visiting to 3. Same goes for 3, same goes for 2. But, but,
2
but
plus 2, 4.
2 is only visiting to 1 by one time here. Then again, it is visiting to 1 again through a different path. The same goes for 3. 2 is visiting to the
Again,
3
again.
by this path, and then it is visiting to 3 by another path as well. So here 2 is visiting 1, not 1, but there are multiple instances through which 2 is visiting 1. So as a result, it is not following our condition of Euler path. As a result, this graph is neither an Euler path nor an Euler circuit. And same goes for this graph if you observe it carefully. So here if we see through, we are going to find out that each vertex is visited by each graph. Yes, they are visited by each graph. So why is this not an Euler circuit? Why is this not the case? I will elaborate you with you this case on how we are using this case to detect whether a graph is Euler or not. So keep in mind, we are going to explain it later on. So now as we have understood what is an Euler path, what is an Euler circuit, and what not is an Euler path, now the question arises that how we can make our compiler of our computer understand that certain graph is not Euler and certain is it. Because by looking at it, yes, by visual representation as a human, we can judge something, we can say something. But for computer to understand, we have to write some code. So for that, we have to derive some logic. So here is a pattern that I have observed while solving this problem. This is a universal pattern when it comes to solving problems related to Euler path. So there is a pattern that is forming in Euler path and as well as in Euler circuit. Okay. Now let's just understand what that pattern is. So here I have created an adjacency table for these graph for the graph that I have written here, the one which I'm circling right now, I have written the adjacency table for this one. So if you understand it carefully, you're going to find out that 1 is going to 2, 3, 2 is only going to 1, and then 3 is going to 1 and 4 is only coming to 3. So that is what I have written here. Now understand it carefully.
Santosh!
There are two things that we have to consider when it comes to solving this problem. First one will be circuit and second one will be path. Okay, and the condition that we are going to apply is that for any adjacent vertex, if its adjacency list size is divisible by 2, then we are going to say that this circuit is forming an vertex, and if that is not the case, then we are just going to increment that thing as our path. So let me just elaborate with you. In this case, we are going to find out, we are first of all going to traverse, and we are first are going to be on node on vertex 1, and in that vertex we are going to find that it had 2 as its vertices where it is actually going, and by applying the logic of %2, that is the size of it is 2, so 2% 2 we are actually going to get 0. So as a result, the circuit varies actually not the case. It is like 1% 2 is not actually giving us 0, it is actually giving 1. So as a result, we are just going to increment path here. Then we are going to come to vertex 3. Same here, the size is 2. We are going to 2% 2 and the result will be 0. So as a result, we are going to increment the value of circuit by 2. And then for the fourth vertex, if you see carefully, there is only single element available. The same condition will be applicable. So 1% 2, we are only going to get 1 as an answer. So as a result, we are going to increment the value of count. Now if the value of circuit is equals to the value of vertices in this graph, which is in this case is 4, if that is the case, then we are going to say that the given graph is Euler circuit. And if path value is equals to 2, then that graph would be an Euler path. So let me just revise this to you guys. If the value of circuit is equals to the value of vertices in that graph, then that graph would be an Euler. And if this condition is not applying, then we are going to check the another condition, that if the value of path is equals to 2, then that graph would be path. So in this case, the value of path is actually going to be equals to 2. So as a result, this graph of our is an Euler path. Now let's just understand an example to understand the case regarding Euler circuit. So you can see here I have also created the adjacency list, and here are two variables that we have to take. One will be circuit, the other will be path. Okay, so for 1 we are actually going to traverse from top to bottom. So first of all, we are at 1, and for 1 we are going to see that the size here is what, 2, and 2% 2, if we divide 2 by 2, the remainder we are going to get is what, 0. So that is why just increment the value of 1, increment the value of circuit as 1, and the path value will remain 0. Now if we come to 2, the same condition will apply, because here we are also getting the size of 2 as 2. So 2% 2 is what, 0. Again, the size of the circuit will be incremented by 1 and it will become 2. Now when we are going to come to vertex 3, again it is actually going to 2 other vertices, 1 and 4, and size of it is what, 2. So as a result, we are actually going to again do the same thing, going to get 0. So thus the value of circuit will be increased by 1. Then for the fourth vertex, same case, 2, and its value will be increased by 1. Now as I already told you, there are two conditions through which we are going to check a given graph as Euler path or Euler circuit. First one is that if the value of circuit is equals to the value of vertices in this graph, then it will be a Euler circuit. If the value of path is equals to 2, then that graph will be an Euler path. And if that is not the case, if neither of these conditions are applicable, then the given graph will be nothing, null. Neither it is Euler circuit, neither it is Euler path. So that is what we are going to find out. We are going to figure out in this case. After traversing through this graph adjacency list, we are going to find out that the value of circuit is 4, and the number of nodes, number of vertices in this graph is also 4. So vertices is equals to v, that is 4 is equals to v. So as I already told you guys, if this condition is applicable, then the graph will be Euler circuit. And as you can see, this graph is actually an Euler circuit. Now, as we have understood, there are two conditions through which we are going to judge a graph, either it is a Euler circuit or not. The first one will be that the value of circuit after doing the for loop, after doing the traversal, it should be equal to the number of vertices in that graph. If that is the case, then that graph would be an Euler circuit. If the value of path is equals to 2, then that graph will be Euler path. And if neither of these condition is applicable, then that graph would be nothing. And as we can see in our case, so as I already told you, I will explain about this graph in a moment, and that is what we are going to do. So two conditions that we are looking, guys. There is a variable name circuit, there is a variable name path. Initially their value is what? 0. Its value is also 0, its value is also 0. Two conditions we are looking at: the value of circuit, if it is equals to vertices, then it will be Euler circuit. If the value of path is equals to 2, then it will be Euler path. If neither it is case, it is nothing. Okay, so that is what we are going to traverse. Now this is the adjacency list of our graph, and as you can see by visual observation, we are actually finding out that each vertex is actually visited once. So if you traverse from 3, we can come to 2, from 2 we can go to 5, from 2 we can go into 1, and we can go to 4. So by visual representation, this graph is looking like an Euler path. But now we are going to understand that why it is not an Euler path. So if you see carefully, we are actually going to traverse from 1. So for 1, we are understanding, and we are seeing that its adjacency list size is 2. So as I already told you, if the adjacency list size, when it will be divided to 2, if it is equals to 0, then we are simply going to increment the value of circuit. That is what we have done. Then now we are going to come to vertex 2, and here the size of this vertex is 3. So as you can see that when we are going to divide 3 by 1 by 2, we are not going to get 0, we are going to get 1 as a remainder. So if that is the case, simply increment the value of path. Now we are going to come to vertex 3. So for 3, again, its size is actually right now at the moment equal to 1. And if we are going to do that way, so 1% 2 will always be equal to what? 1. So again, the value of path will be increased and not for the circuit. The same goes for 4. Its value is what? 1. 1% 2 is going to give us 1, which is not equals to 0. So again, the value of path will be increased. Again, for the fifth vertices, the size of it is 1, this condition, and as a result we are going to get the value of path to be equal to 4. Now these are the two conditions through which we are going to find out that whether a graph is Euler or not. So as you can see, the value of circuit here is what? 1, and the number of vertices in this graph is what? 1 2 3 4 and 5. So there are 5 vertices, and the current value of vertices is what? 1, which is not equal. So as a result, this graph is not an Euler circuit. Now comes the point of Euler path. Let's just see. So as you can see, the value of it is right now 4. So the given value that we have found after traversal is 4, and what we want was 2. So we are not getting that value. As a result, this graph is not an Euler path. So as I already told you, if the graph is not an Euler circuit, if the graph is not an Euler path, simply return 0, and the graph will be just a normal graph. That is what we have to do in this question overall, guys. It is a very simple question. Just we have to figure out either a graph is Euler path or either it is a Euler circuit. If the graph vertices are only visited once throughout the traversal, then that graph would be Euler path. If it is starting and ending at the same vertices by going through each vertex is only one, then graph will be Euler circuit. And if both the conditions are not matching, then we are simply going to return that this graph is not an Euler circuit. And the condition through which we are going to check that thing is by taking two variable named circuit and path. And for circuit, the condition would be that the value of length of our adjacency list should be equals to 0. If that is the case, simply increment the value of circuit. If that is not the case, simply increment the value of path. After doing that, there are two conditions to be three, that the value of circuit should be equal to v, the number of vertices in this graph. If that is the case, then the graph is a circuit graph, Euler circuit graph. And if the value of path is equals to 2, then that graph is an Euler path. And if neither condition is matching, then that graph is simply going to be neither Euler nor circuit. So now let's just write this code down. So as you can see, I have already written this code. So first of all, the thing that we are looking at, if the graph is null, then there is no point of checking that either it is Euler or not. And simply just return null. That is what we have done. Then we have taken two variable. First of all is path. The second one, first of all is circuit. The second one is path. Then after that, we are just going to traverse through the adjacency list of this graph. And what we are looking at, if the size of the adjacency list when divided by 2 giving us remainder 0, just simply increment the value of circuit. If that is not the case, simply increment the value of path. And if circuit is equals to the number of vertices, return 2, because that is what they are asking. Return 2 means that it is an Euler circuit. And if the path is equals to 2, then simply return 1, because that means that the given circuit will be our Euler path. And if nothing is the case, then simply return 0, and it means that nor circuit and nor path. So now let's just apply this logic. Now guys, this is the logic that we have developed, and if it is not going to work, then it will tell us that what it is and why it will not. And if it will not work, then sorry guys, I just wasted your damn time, guys. So let's just see. So as you can see, perfectly fine. Yes, you can solve this question via DFS or BFS traversal, but it will be a little bit lengthy process. So this is the most efficient one and simple one that I have found till now. So with that guys, today we have solved both questions, GFG and Leetcode. Along with that, over to you, Shivam.
So yeah guys, thanks for joining with us. We will catch you up again tomorrow.